Okay, welcome back to the next module. It is time we move on from planar scintigraphy to the other two nuclear medicine modalities, which are SPECT and PET. So, as you would notice, in if we have to draw an analogy to what we did in X-ray based modalities, we first did X-ray physics and then we covered X-ray projection radiography, and then we talked about getting the tomography, right, slice. Similarly, we have done now gamma rays, so the physics of gamma rays, and then essentially the radioactivity aspect, and then we covered the projection scintigraphy or planar scintigraphy, very analogous to your projection radiography. So, now in that regard, we will now move on to the modalities in nuclear medicine that has a tomographic reconstruction part. So, in some sense, why I wanted to elaborate on that before we jump in is conceptually is very similar to what we have done with X-ray base. So, now that we have covered planar scintigraphy, the PET and SPECT, what we will do is contextualize to this particular setting. Otherwise, the concept of how do you do the tomographic reconstruction, right, is almost similar. We will use some variable changes, but otherwise it is similar to what we have covered already. So, we have scintigraphy. Now, how do we, so we know what signal is recorded, the gamma rays, how it is recorded in planar scintigraphy. So, we will start from there with the scope of seeing what is the acquisition, first instrumentation for SPECT and PET, and then the imaging principle more specifically to do with your tomographic reconstruction. Okay. So, let us start with the instrumentation. As you will see, this is a typical SPECT system. What you notice here is, apart from the patient table, right, you notice this arm. In planar scintigraphy, we were talked about this Enger camera, right. So, which was flat, and we saw this, that was your planar scintigraphy. Here what do you notice? This is a dual head system. So, this is one camera, this is another camera, it has some angle. Of course, this is flexible, you can make them 180 degrees, right. So, this is attached to this arm and this can move around. So, you have a patient lying here, you can move around. So, the same principle of what did we do in tomography in X-ray? Oh, we had to get data, we got there in one line, and then we moved from different thetas. So, we ended up acquiring G of L comma theta, if you will recall, we will connect back to that. Okay. So, here we start with scintigraphy, planar scintigraphy concept. Only thing that we add on to the instrumentation is this planar. Of course, here is an example of dual head system. You could extend the same one head, one planar scintigraphy, the Enger camera, you can put it to an arm and that can rotate around, right, different directions, you can get the planar scintigraphy data and then do the reconstruction. So, this is the difference. Of course, because of that, because you have to do reconstruction, there are some small detailing that needs to take place, but otherwise is very similar, right. We did similar to CT. Here you have a Enger camera that is rotated and you get the photons, gamma photons in this case, right. We get it from different paths because the radioactivity is sending in different directions. You move the Enger camera, get it from different locations, and then we should be able to reconstruct it. Here, because of the way it is done, you have your collimators. Of course, we will think about this parallel hole collimator, right, but you could also have your diverging, right, the other types that we talked about. So, you can think about having a fan beam in some sense. So, we will talk with parallel hole, so that it is straightforward to what we covered in our X-ray CT, right, at least the introduction material before we compensated it for fan beam. Okay. So, we will do parallel hole. So, I showed you example of two heads. So, you could have more than two heads, but again it depends on, so the radioactivity per se, unlike in your X-ray projection radiography, the source, you excite the source when you want. So, you move, excite the source, you move, excite the source, rotate, excite the source, whereas here Radioactivity is there inside the body, you have prepared the patient. So the radioactivity is sent in different directions. So in some sense, signal is coming on. It is how fast you can capture from different locations, that is the key. So you could have multiple heads, meaning multiple planar Iyengar camera at different angles, and you could record. But typically in that sense you could think about having it full throughout the body. But usually what they found is there's a trade-off, right? So it becomes very cumbersome, very expensive to do all that. So usually 2 head is reasonable, especially the configuration that I showed. You can make it flat 180 degrees, so you can do whole body scan with the same thing. So there are essentially it's brute force, multiplication of the number of Iyengar cameras. You can get fast recording, right? At any particular camera you are going to get the radioactivity based on how much time you are recording. That part doesn't change, but simultaneously you can record using multiple heads. So that way your acquisition time, especially if you want to do whole body and so on, right, your acquisition time can come significantly less. But our focus will not be on all those are extension with brute force. We will be interested in seeing how do we get one tomographic slice, right, one single photon emission computed tomography. So having said that, the idea here is because you are going to do the reconstruction, your camera here should be little more sensitive, right? So it has to be little more better performance than your planar scintigraphy, because you are using this as an estimate to you get a unknown, right? You are trying to get the source where it is radioactivity is coming from. You are trying to locate the source where the radioactivity is coming from. So in some sense there are some minute details that have to be taken care, but we will not worry too much about that. Okay, we will worry about, okay, the camera, collimator, all that is fine tuned, and therefore how do we get this data, what is this data, how do we get the recon. So this is for your SPECT instrumentation. As you see, there is nothing new here. Okay, you know the data that we get, which is your Iyengar camera, you get the gamma rays detected. The Iyengar camera we did in planar scintigraphy. So from an instrumentation perspective, SPECT borrows heavily from your planar scintigraphy. So let us quickly look at PET also. That way we can get into imaging equations, we can make the differences. Okay. So PET, recall that here you have a positron, but in some sense we are not really, so we give the radioactivity and then there is this positron decay or a beta plus decay, but we are not really imaging the positron, or we are not capturing the positron. What happens is this positron annihilates when it moves, it interacts with the free electron, it annihilates there, and therefore you get this free 2 gamma photons. And the beauty about this is these 2 photons that are coming out, they are exactly opposite, like 180 degrees in direction. So they go in opposite directions, and it also turns out to be, oh, you are talking about electron. So electron has a mass, right, and then a velocity. So you can get an energy. So the rest mass, right, kinetic energy from that is half m naught v square. So when you do that, these photons that are coming also have the rest mass energy equivalent for an electron, which is 511 kilo electron volt. So the important detail in positron emission tomography is here also you are ending up detecting only the photons, gamma photons. However, it has a specific energy which is 511 kilo and more importantly, if one decay happens, you are going to record 2 photons at 511 kilo electron volts that are exactly in line, that is exactly 180 degree in direction, and that is a key information. So you might think, okay, this is a gamma energy as well, so why cannot I just use whatever we did already, single photon emission tomography. Instead of one camera, I can probably have 2 Iyengar cameras on the 2 sides and then go about the same way. I mean, it's a gamma photon. I know my gamma camera is there already. So I could essentially do that. Along with that, as long as we are able to, right, we can do that, right, you might imagine that. So along with that, if you can able to say when these two are hitting, that is the information that we should probably use as well. So a typical PET scanner looks something like this, nothing much different, everything is enclosed, it looks very similar to your say CT or an MRI. I mean, at least you have a bore, right, you have a gantry, and then the patient table can go in and come out. So very similar, but what is inside, apart from the detectors, right, we talked about, there should be some way and mechanism to detect this 180 degree they come. So they have a decay, they go in two different directions. So if I catch photon in two different directions, is it simultaneous, is it coming from the same activity, that judgment we should be able to do. Okay. So we talked about this, we have, apart from the detector and stuff, the important key feature here is the ability, the positron itself gives rise to these two photons. So the idea is, from the radioactive decay, the positron comes out, but then it annihilates with an electron and you get two photons of 511 kilo electron volts. So if you are able to detect these two and you have a very good timer circuit when these two are getting hit, right, then I may be able to say whether they are near simultaneous. If they are near simultaneous, along the line that is joining the detector is where this activity has happened, right. So it is coincidence detection circuit. So this is a very integral part and important part of your PET instrumentation, and this is very important because we are going to use this information to our advantage, and that information is, if I get a activity, can I get another activity about the same time on the detector that is exactly 180 degree on the other side. If I can get that, then I know that activity has happened in the line, right, connecting through to the two detectors. That much I can say. Okay. So you see the advantage here. The advantage, unlike your SPECT, when you use the Anger camera, there you have to have, you don't know the source, it can come at any angle. So essentially you have to have a collimator. Whereas here, and therefore what happened, because you have collimator, you also reduce the number of photons that are captured, right, because your collimator is taking some and it is reducing, in the spirit of reducing the Compton scattering, it also reduces signal, right. Whereas here I don't have to worry about that, I don't need to have a collimator, I will let all the photons come and get detected. So I can increase the sensitivity. After I detect it, as long as I can go back and say which two photons, right, hit simultaneously, if I can have a threshold, then I can say in timing, I can say these two are near simultaneous and therefore they correspond to the same activity along the line. So in that sense, I don't need to worry about my Compton scattering. So I can remove the collimators, right. So detect two events in opposite direction occurring simultaneously. Of course, the simultaneous is, what is simultaneous, within some tolerance. Okay. So you can have an activity here. So you have a detector. So if you detect, so you will have activities detected, right. So if you can go to the circuit and that is able to tell when these two happened, right, and if it so happens that it is within some short, because simultaneous means it is not exactly the same, there should be some tolerance, right, because it is on different location slightly. So simultaneously is measured in terms of this tolerance in the window. So 2 to 20 nanoseconds. If you detect an event in this detector and you also detect an event in this detector, right, and they are within the small time window, then I will say probably the activity is happened along the line connecting these two. So now because of this, I don't need to worry about my collimator. This circuit is going to help me get as much signal in the within the photons that are detected, what are the true photons that we want to worry about, right? That is made sure based on this window threshold, okay, and therefore your sensitivity increases way better. Also notice one another difference, even here probably you could see. So you expect that there need not be collimator. So if I am to use the same argument of spect, planar scintigraphy, essentially when we came to spect, the same angle camera can be rotated. Now instead of having only one rotate, if I can have two of them and then rotate that, maybe I can detect simultaneously and then do the coins. So from a logic point of view, that is fine, right? That is what it is doing. But then there are key differences here. What are the key differences? One of the thing is your coins, you want to do this, so that is fine, you can modify that instrumentation, but then you don't have collimation. So if I have to use the same instrumentation for spect, right, then I have to take the collimator for one study, put the collimator for another study. That is one thing, and then so that one inconvenience, but then that is an inconvenience. But then there the gamma can be any energy that is coming, right? Even though you have the tracer, it has a energy that you are looking at, it is coming. Still there is this Compton scattered one that comes at lower energy, right? So we saw about that Z pulse and how we try to reduce that. Here you are very specific, you are looking at 511 kilo electron volt that is coming, right? You are not really worried about the radio tracer per se, right? You are looking at only one energy. So maybe the detection part, instead of using the same angle camera specification and the materials, where you had to have a host of different energies, no, it has to be good so that it can cover different radio traces. Here I don't have to do that, I don't have to compromise on that. I know there is only one energy that is going to come, which is 511 kilo electron volt. So I don't need to really use the same, say we talked about sodium iodide, right, with thallium. We don't really need to use a generic one that can be ready for different radio tracers. I can actually get something very fine tuned for efficient for your 511 kilo electron volt. And therefore what happens is the detector here is slightly different. Instead of using just the Anger camera with one crystal, which is of that the head that you saw, right, so big, here we could do little better because of the known requirement. So what we have identified is you have this coincident circuit, so I need to be able to do this localization, coincidence. So there are three types of signals that you can get or activities that you can detect, but you are going to weigh only those activities which are true. What do I mean by true? I should have a another photon detected within that short time interval along the detector that is on the opposite side. Only if this happens, then that is a true. You could always have, here also there could be some noise, like for example it could be due to scattered, right. So it is going there, scattered, it is coming here, that is a possibility, or this is actually going there, some other activity is giving here. So from your timing circuit, so this is kind of a random. So from a timing circuit there could be random, right. You are picking some other activity, this is getting some other activity within the time interval that you have. We cannot do much about that, but what you can do is these things you can avoid. So if you have a scattered, if it is scattered, the energy is reduced. So at least the scattering that is happening within the crystal after it comes to the crystal, right, we can reduce. So when will that crystal, how does this happen? So we are, okay, from the body is one story. The other part that we saw when we covered Anger camera is your crystal, the thickness, right. You want the efficiency to improve, so if you increase the thickness, what is going to happen? You are going to have Compton scattering from the crystal, right, before it goes into the photomultiplier tube and get amplified. So at least that we should be able to reduce. How can we reduce that? Maybe we can go for a thinner crystal. But if you go for a thinner crystal, maybe it is not catching the gamma photon, right. So since we have coincident circuit, that is a blessing, but how can we reduce this probability? Maybe we can go for a better crystal property that is very efficient at this particular 511 kilo electron volt, and therefore here, right, here the crystal material is usually bismuth germanate, right. So here you notice it is very tuned for 511 kilo electron volt compared to your say sodium iodide, right. Compared to your sodium iodide, this has 3 times stopping power. That means it can be thin 1/3, right. So it has its advantages, you see. So the idea here is, principle is same, how we did for SPECT, same gamma principle, gamma ray detector, but then here it is fine tuned only for 511 kilo electron volt. That is an advantage that we can do. And that way the idea is, oh, if I want 2 crystals, right, if I want them to detect, maybe intuitively we might think, why don't we have a small detector and many of them, then maybe we can better localize. But then the challenge is, the smaller, we saw about the pixel signal to noise ratio, right, in nuclear medicine, that will become a problem. So in order to avoid that, what PET does is, it does take the advantage of both. So it has one block, so you have only one, right, you have only you have a big detector constructed based on several blocks, and each block you have these 4 photomultiplier tube. This is one block that is shown here, okay. So this block is basically your crystal plus your photomultiplier tube. So this is like your previous one, this is like your previous one. You have a crystal and then back of it you have your photomultiplier tube, and then we will use this idea of x comma y, remember z pulse x comma y, so that we can get our x comma y localized center of mass calculation, z pulse, right. So you could use that to your advantage, and therefore this is a nice combination. You want to have single crystal, but at the same time you want to have better resolution, and therefore here material is different and the configuration of your detector is also slightly different. So here we go for a ring, right, ring detector, because you want to simultaneously detect, you do not want to have some rotation and waste time. So you want to have your ring detector, but in the ring detector, if you have each of these crystals, right, in some sense cut and arranged like this, that becomes complicated and you might lose your signal to noise ratio. So what they have done is, they have used a block. So this one block is one crystal, that one crystal has 4, in the example shown we have 4 photomultiplier tube, and therefore what is nice is, you could be able to still localize within that crystal. So you can get your good signal to noise ratio and better resolution, because you are able to correct for your x comma y, and you have several blocks. So this arrangement provides multiple benefits for the reason that we talked, that is one thing. And then you notice, in some sense, that way you could see this ring, right, you could visualize, exaggerate, visualize several slices, right, I could get several slices. So in fact, in one configuration, if you really want only one slice, right, when you go one slice not to affect the next slice, you could actually have something in between, right, that can shield inter detector, okay, along this annular, okay. So you have this idea that you have benefits of both one single crystal block, but then you also have several different blocks, so that you could write several different blocks that will allow you to get more. You can do 3D volumetric, or you can do planes that are stacked next to each other, right, you could do any of that, okay. So this is a unique configuration compared to the other 2 modes that we have seen in nuclear medicine. Therefore typical numbers, right, so you have something like this, you have 8 subcrystals, so your each crystal is about 2 mm cross 2 mm. But then we are talking about several blocks, each block has 2 cross 2 photomultiplier tube. So what we saw is 3 major rings are formed, right, that is based on the block. But if you look at the each one has 8. So that means you can look at each block has 8. So you can look at it as 24 detector rings. Okay. So typically there are 48 detector blocks per major ring, so along the circumference. Okay. So this is involved, intricate, so the instrumentation is a little more complex than your other two, but then here you can do a better job. You have versatility, timing, right. So you have lot of 384 detectors per ring and so many crystals. So now otherwise the instrumentation, the concept of what each one does is very similar to what we covered already in the planar scintigraphy. Okay. So there is nothing more to the instrumentation part of it. So once we are through with instrumentation, now we are ready. So we know something happens, the activity happens, it comes and hits the detector, so I can collect, right, on the detector. So now what do we need to do? First is recall our imaging equations and then do the reconstruction. Okay. So before we jump into that, just while we are at instrumentation, it is also fairly common to have nowadays, you have what is called as PET-CT. Remember, PET is a functional imaging system, whereas CT, as we saw, is a good for structural imaging, and therefore they have found it to be very useful. They as in the clinical practitioners have found it to be very useful when you have both of them well registered, so that you see the anatomy and the activity there. That gives them lot more insight into the problem that they are trying to, clinical problem that they are trying to understand. So there are PET-CT instrumentations. First guess would be, okay, I have the patient get your CT, then do your PET, and then we can register these two. That's a traditional approach. Okay. However, there are now systems which are integrated, where you have combined PET-CT, where you have both, right, so that the patient does not move from one location to another location. So the advantage of this is, of course, you can make the registration problem very easy. This is very important because especially when you are going to do some study where you want to see how the heart is behaving, right. There the heart is there, motion, so you want to do it fast. So it is prudent that you have it in the same location. That way it might be easier to do the registration. Of course, you can do the reconstruction later. After you acquire the data, you could still go back, or you could have some gating like we discussed. So we could always do the reconstruction later, but at least acquisition can be done simultaneously or at the by the same location. You don't have to move the patient to different instruments. Okay. So with respect to instrumentation, this is what it is. Now let us get to our imaging. So given this instrumentation, you have detected. So where is the patient? Here is the patient. What do we want to see? Oh, we want to see tomography. So axial slices is what traditionally, right, we are looking at. So that means I have to first get my coordinate system correct. You will notice that in CT as well we did this coordinate system. So it will be fruitful for us to make sure the coordinate here corresponds to the way we set it up for CT. So you have an isocenter where the patient is, and then you have L comma theta was your data format, if you recall from your CT, X-ray CT. So here we would like to have a similar setup so that we could quickly use the reconstruction algorithm that we already have. So here is the setup. So this is the camera is going to move around the patient. So, these are going to be your coordinates. So, you have your R, distance from the center of the patient to the detector, right, that is your capital R, and you have this L, Z, oh, Z is going from head to tail. So, your you notice our imaging equation that we did for when we begin our gamma rays, right. This is what it was. We said, oh, the detector is here, the gamma rays could come anywhere, and notice here we were drawing this with respect to the detector system. So, this was your Y, this was your X, this was your Z. So, when we did this material from a detector point of view, what is detected in the imaging, in the physics part in nuclear medicine, we wrote imaging equation in this coordinate system, whereas it will be prudent now that we want to actually, because there the image was this plane, right, there the image was your X, Y, that is why we wrote it like that. But here what is going to be your image? Oh, your image is going to be through the patient, it is a slice. In CT, if you recall, our image was still X comma Y. So, we would like to go back to have analogy with the CT, and therefore, we would like the image, the slice to be X comma Y. Whereas, if you take the slice here, it will not be X comma Y, right, it will be Z, Y comma Z. So, it will become inconvenient, right, we will get lost. So, what we will do is upfront we will change the variables, right, coordinate system, so that we can get consistent with our reconstruction formulas that we did. So, we will now write it in terms of this coordinate system, the isocenter, and what we need to do then is from here what we had the imaging equation to what we want, so that we can recon in X comma Y. We look at this and say, oh, this Y is L, right, oh, this X is your Z, okay, and your Z is your this direction, right, Y. So, we recognize this, make this substitution X to Z, Y to L. So, we have this imaging equation, go back to our nuclear medicine imaging equation that we did in the physics part module. So, we had the equation already. All I am doing now is recognizing this coordinate system for your data acquisition. We are going to change the variables so as to be consistent with our CT X comma Y, because here also our recon is going to be, image is going to be X comma Y. So, it better represent the axial slice. Okay. So, this is the variation. If you do that, the same equation I have just changed the variables. So, with this equation we got before. So, phi of Z comma L is, you have this A of X comma Y comma Z is your radioactivity. Again, here we have not really changed much, the radioactivity we have left it as A of X comma Y comma Z, patient coordinate. So, we will not we will not worry too much about it right now. It is a 3-dimensional, right, we leave it at 3-dimensional here. So, we do not change the variables here, it is only the detector that we have changed it in respect to this coordinate. And then you have your decay term, right, because it is coming, the radioactivity is coming from within the body, it is crossing through the body. So, body to the detector could have some attenuation. Okay. So, this is our equation, just doing this substitution. So, what we need to do now is, our objective is eventually to get transmission slices, right, tomographic slices. That means A of X comma Y comma Z, I am not really interested, each different slice is different. I want one SPECT image or PET image, I mean is one slice. So, I just need to worry about X comma Y. So, A of X comma Y is what I want. I can locate at different Z's, I can be at head or I can be foot, that is fine. Okay. So, we will not have to worry about this variable Z, we can make this a plane, which is what we will be interested in. Okay. Imaging is what we are not interested in volumetric, we will do only slice imaging here. Okay. So what we need to do is with this, right, with this case that we have, we should start to write our imaging equation. How do we do? Initially we know, looking at the system, your L can be written in this parametric form, right. This is we covered this even when we did the CT. So, but then here what you notice is we want to vary. So, we could write it in terms of S. See, what we have right now is theta equal to 0. Just to go back a little bit. So, you have your theta equal to 0, right, we have it. But when you, so in that regards, if you look at it, your what you are getting in the detector is integration through your y direction, right. But if I take theta at some other angle, it need not be, right. If you take it 90 degree, then you are integrating along the x axis, clear. So, that is a subtle difference, but important difference here, because unlike your CT where the source and detector moved around the patient, here the source is within the body, only the detector is moving, right. So, your line integral, if it at 0, it is going through your y direction, whereas if you go move around, it may go through some other direction. So, this is not right. So we would like to write it such that we account for that. So, how do we do that? You have your L comma theta, right. So, instead of writing that, we will say we can write it in terms of S, right, in terms of S, and therefore, you notice from here we could do this transformation. So, at any particular theta, you can start to write, right, this is your camera. So, this is your location. So, you are moving. So, which element that is along L, correct. So, there is this L, parallel lines, how are they separated, right. So, this is your L, and at whatever angle your detector is located, right. So, this is your theta. So, you can write it in terms of S, right. So, x of s. So, this is another parametric form where you write it in terms of L and S. Okay, what is this advantage? Now, you are not, you know how it is moving around, right. So, you do not want to write it in terms of y and x, because theta is changing, you want to account for that. So, if you do that, then we could substitute, right, in phi of L comma theta, you could substitute these variations. All of this is substitution of your change of variables, right, within the limits. So, you have your A of xs comma ys. So, we have dropped z as discussed. We will talk about only one cross section, right. So, we have dropped z for that reason. Now, this is our imaging A of x of s comma y of s, and exponential is coming through that. Okay. So, what do you have? Okay, fantastic. I have, this is my data that I am recording of this. What is your known? What is your unknown? Oh, this I can get. Rest of it I can, R and all is fine. But the problem is I have to go after this guy. This is what we want to find. We want to find the radioactivity along the line or along the slice. But what do you have? Oh, you also have another variable, which is your mu. See, the whole of X-ray projection radiography, we talked of X-ray CT, we were only going after this guy. So, we had this equation, we were going after only one unknown. Now, you have two unknowns. I am actually interested in going after radioactivity. I am not really interested in this now, I am interested in this, but this is also an unknown. So, this is very tricky. How do you solve the problem, right? Well, I need to have some additional information. If I can have additional information about this, maybe I can solve for this. Okay. So, you have two unknowns. Not only that, the problem is there is also this depth dependent, right. You have your R is this direction, right, R, S is along the R. So, where it is located, so that there is an inverse square law that is affecting as well. So, there are two problems here. One is I have mu which is an unknown, and I have some factor here which is dependent on the which could contribute to the inverse square. I have a problem, I want this guy. How do I simplify the problem? If I have additional information to simplify the problem, then perhaps it will become tractable. Where is that information? Well, I mean, it's easy to question, but when I am here, what will I do? Oh, okay, what do I know before this? Well, okay, I am starting out, what is the easiest way? If I do not really know this mu, what can I say? Well, I am not worried about mu, I do not know. So, I will pretend there is no mu, okay. I will pretend there is no mu. There is no body, there is no distance, attenuation, that I will not worry. I will just make my reconstruction based on what activity that I detected is just based on the activity that is happening, not accounting for the attenuation that it would have gone through. That is one ignore the mu is one solution. You will be surprised, that is the most commonly used approach, because given what it is, it still is reasonable that you are getting some information that you did not get otherwise, right, with the nuclear medicine, functional imaging. So, they were actually able to live with this, doing that approximation or simplification, whatever you want to call it. Okay. Of course, if there is any other way that we can get our mu, then maybe I have my mu and therefore the only unknown is going to be this. So, I can collect this from different L comma theta and do our regular CT. Okay. So, let us just look into first bold approximation. What is the bold? Ignore mu. Okay. Ignore mu and all the scaling inverse square law, do not worry about that. See, you are not really going for any quantitative number, you are going for the high radioactivity, less radioactivity, that is good enough, that is the first level information that you are getting. So, really, these are details which are complicated, but it turns out this bold approximation still is very powerful and it is very useful. That is, they are able to get a recon that is reasonable to do clinical diagnosis. So, if you do that, what do you get? Phi of L comma theta is minus infinity to infinity a of x as y of s ds. How does this look? Essentially, it is saying I am just integrating from minus infinity to infinity, right, along this object a of, along this line a of xs comma ys of ds, along this line. What is your phi of L comma theta? So, this is what does this? It is a line integral, right. So, along this line is projected onto this point. Haven't we seen this before? Right, we have seen this before. Oh, this is your, can be seen as your Radan transform, right. Only thing is we used g of L comma theta, right, that is what we used. Maybe but otherwise we already see there is nothing fancy about this. Now we have Radan projection, I need to, right, I have a collection of phi of L comma theta, I need to get my a of x comma y, right. So, how do I get my a of x comma y? First is we can convert this to our x comma y using line samples. You have it in S, in that plane you want to go it in terms of x comma y, you can use line impulse, right. So, this is again the S to x comma y, we have done this before as well. Okay. So, you can write this phi of L comma theta is a x y, you have used the delta function to pick it, that is along that line, that is what was written here, right. So, this is nothing, if you look at this is nothing more than very similar to your g of L comma theta, and here you had mu or f of x comma y. If you really go back to the start of the CT, this is your f of x comma y, the ground truth object, that you want to go after. This is your estimate of your projection, g of L comma theta. So, given g of L comma theta, measured g of L comma theta, you want to calculate an estimate for f of x comma y. Here it is a of x comma y, right. After this there is nothing, it is very similar to what you did before. Subtle differences, of course, there is some scaling factors, and then there your g of x comma y was logarithmic, right. You had I by I naught ln of. So, we had the g of x comma y had to be converted to that logarithm, whereas here you do not have that. But apart from that, this is essentially what you collected, this is what you want to get tomography. So, you can end up reconstructing using whatever filtered back projection approach that we covered earlier. Okay. So, this is actually turns out to be very powerful and useful. Of course, if you say no, I want to correct this because this is I had a mu, right, this is disregarding the mu, can I do any better? Yes, you can do better, there are few ways you can correct for that. One of the ways is you get a corresponding image from your X-ray, CT or MRI, right. So, you can get an estimate for mu. So, if you get an estimate for mu, then you can get that, you know, roughly for each location. If you get that, you can use that information. Or another way to do it is, okay, I will have some calibration way, right, use known strength gamma emitting standard and then collect the imaging data. Okay. So, I will have a known strength, the radioactivity is not inside the body, I will have a known strength and then some tissue and then your detector, then I know my known strength, I know the path, I can get average mu. Okay. So, I can do that, that is one way of doing it. So, you have to get the information from somewhere else, okay. It is a different experiment that you will have to do. Another approach is iterative image reconstruction, which is currently gaining much popularity because all these computational advances, right. So, we will guess, make an initial guess, right. In one iteration I will treat mu of x comma y as a known. So, I will have some guess start for my mu, okay, and then try to get my a, but I am not happy. So, once I get my a of x y, in the next iteration I will treat a of x y as a known and try to solve for mu of x y. Likewise, you iteratively do this until some optimization you say, okay, this is a threshold on which you stop iterating because this is probably, you know, the a of x y estimate is close to your ground truth a of x y based on some error criteria, okay. So, or your cost functions. So, this is a popular way to do it, but like I said, these are new age, majority you can still get away with, they get away actually with disregarding mu, okay. So, there are several applications for SPECT. Brain, again brain is an active organ where we always talk about cardio, but then brain is very important opportunity because CT, remember CT was a deal, it is in the skull, you have to go through the skull, that way CT got popularity. Projection radiography, especially for brain, soft tissue, okay, for brain was a challenge because your skull would take all the pixels. So, CT was very powerful to start to see inside the brain, but that is structural. So, we want to see the activity as well. So, brain is a very important functional aspect, imaging for the brain is an important application, tumors, right, and the rest of it is the usual suspects, your heart, respiratory, liver, kidney, right, you could do all of this. So, this is quite popular, but more popular is your PET, okay. We will see why PET, what is the imaging equation for PET. So, we know it is a similar projection, you get the data similar, right, the detector, that part is not much different. What is different here is the arrangement. So, we need to make sure that we write our equations corresponding to the acquisition geometry for PET. So, here for example, what you are doing, oh, you have your coincident detector. So, this is what we are interested, we are interested in the line that is going here. So, how do we write this line in terms of L theta? So, along this line there is a radioactivity that is happening. This radioactivity is happening. So, you have this n number of photons, right, the gamma photon coming hitting here, gamma photon going hitting here. Okay. So, before we jump in, let us see, it is a probabilistic thing, right. You get your decay gives your positron, positron catches an electron and gives photon in two directions, right, 180 degrees apart, but it can be in any direction. So, it is a, so number of photons that you detect is going to be having some probability, right. So, what is the probability that the photon is going to hit the plus here, plus direction, right. So, probability of photon reaching the detectors, right, because first is what is the probability that is going to hit this detector. We can get that as, oh, you have this radioactivity, right, N0 is the one that is coming out. This N0 has to go through this tissue with attenuation mu. So, it is starting with S0, it is going till R, right, upper limit, whatever loss is there is your mu of along that line for that particular energy, clear. So, this is something that we knew from before, nothing fancy. So, this has to happen, right. So, this has to happen. What should happen? Oh, then what is the probability that it is hitting on the other side? Very similar, n minus of S0 is similar thing, only thing notice that your limits are slightly different. So, here we are writing instead of S0 to R, we have written it from R to S0. Okay. It does not really matter, this is along the line. So, the gradient takes care of it. So, if you can write it as minus R, then it will work out to be very similar. So, essentially what you are getting hit here, what you are detecting here has come through this line integral. What you are getting here is come through this line integral. Okay, that is what these two are saying. But the important aspect here, unlike your spect, is, see, this S0 is arbitrary location, right, you do not know. You know along this line the activity has happened, right. But the good thing about PET is, because of this coincidence, what you know is this is along this line, that is one good news. The other good news is, if I am to take this activity, whatever I detect is something real, right, that is the object of, that is the activity of interest, then it has to be coincident. And therefore, what is the probability that you will have this and this? Oh, probability of this is this one, probability of detecting here is this one. So, probability of this and this is going to be multiply this into that. Okay, so, this has to happen and this has to happen. So, quickly you notice, even though it looks big, the advantage is you have exponential into exponential. Oh, you can sum the exponent, what is there inside the exponential, right. E power x into e power y is e power x plus y. So, if you do that, what do you see? Oh, essentially these are same, x of s is the line, but your limits have changed from R to S0 to S0 to R. What does that mean? Oh, I have minus R to S0 to minus R, there is a minus R actually, okay. You can combine that, you get the full path minus R to plus R, okay. So, NC coincidental is nothing but N0, the activity that happened there, and exponential of loss over that path minus R to plus R. So, now you see the advantage, at least maybe you do not see it yet, but you can recognize already that this is a big deal. This is simplifying our problem little bit. All this multiplication, that coincident criteria helped us get this limits, which is from minus R to R. So, in some sense what you are recording is total loss along the line here. We will see, if you are not able to spot the advantage of this, we will see it in one more slide. Okay, so this is what we are. So what is our real objective? Our objective is not just N naught. This is the probability with which you are going to get the activity detected. Our interest is, detector is measuring this radioactivity. So you are catching this activity over time. That is, you are integrating, say whatever the source is giving out this activity, this photons, you are catching those photons over time, right? That is your detector's job. So we can write our imaging equation instead of N. This is the probability of getting hit. Our actual data is integral of this, right? You are catching all the photons over time, right? So what you have is a configuration like this, right? You have your L theta and a particular theta. So these are the lines, this minus R to R. This is what we are catching, right? So in this configuration, so what do we write our imaging equation? Phi of L comma theta, right? Phi of L comma theta is nothing but all the scaling factors, effect of geometry, effect of this, that you can put here, detector efficiency, all of that you can put here, some constant, right? But more importantly, you notice you are integrating from minus R to R of A of xs ys, right? Instead of n, I have expanded the to integral of this guy. Along with n, we had the probability of detection, right? So there you had your exponential within minus R to R. So now notice, even though this looks two integral and this looks little complicated, in SPECT also we saw similar and we said this is an unknown, this is an unknown. So we had a problem. So similar problem we also have here. But one subtle thing that we could, which is better here, is your integral minus R, limits minus R to R, right. So what we can do is, this is not dependent on where the S is. See, that is the beauty. This is not dependent on where the S is. It is not a variable with S, right. So wherever the radioactivity, that is, does not matter, wherever this mu, it is the integral through the mu, right, integral along the line from minus R to R, that is important. So we can separate this term, right. So you have your phi of L comma theta, k of this ds, only your radioactivity term A of x comma y ds, that is the thing. This one is just along the line of the whole object. So what this, why this is advantageous is, you actually do not have to know the two parts, which part is more closer to one detector, right, that you do not really need to know. All I am interested is in total attenuation along that line. If that much I know, I am good, okay. So you do not really need to know where along the line. See, remember, so I could use the projection data. I do not really need to know my mu along the line, right, because this is full minus R to R. So I just need to know the projection of the mu, that much I know. If I can get, that problem is solved. Unlike your SPECT, where you have to have, you should also know the location of your mu, how the mu is distributed along the line x comma y, you should know. Only then you can start one part, the other part, right. Of course, here that is not the problem. So what we can do is, same thing, we will pretend that your attenuation, if you ignore for a minute, right, if you ignore, because it is not a variable here, so you ignore, it is a factor, so we will ignore that for a minute. If you ignore it, you just get phi of this guy, you know this already. Convert this into x, L theta, right, this S, with a similar thing that we did for SPECT, just coordinates, parametric form, you get your phi, okay. So there is no big deal about this. So you can do correction for attenuation here more elegantly than before. How do I say that? All I need is the projection, so I can get that variable, right. So I can get my corrected phi as your phi, and this term, the k into exponential, I know it is exactly at 511 kilo electron volt. So I can do this, I can get it. I am interested only in the projection. So what we can do is, have a source outside, along the line, get the detector, or done, or you can use your PET CT, right? We talked about PET CT is a very common thing. So, from CT you already have for the same registered patient, right? You have your CT image. So, if you have your CT, you can always get your mu and get this integral. So, you can calculate this, no big deal. Okay. So, after you get this, it is just the question of applying your filtered back projection, very similar to what we have done before. Okay. So, you can write your corrected A of x comma, this is your tomographic image, right, of your radioactivity in x comma y plane, right. You get this corrected projection values, nothing, it is your typical filtered convolution back projection. Okay. So, filtered back projection, convolution back projection is what is shown. You can use the same algorithm like before. So, only thing is how do you arrange the data correctly to use the same algorithm that you probably would implement, right. That is the key here. Otherwise, really the details of the algorithm reconstruction is very similar, or if you understood the CT, X-ray CT, it's a careful extension of that. Okay. Likewise, PET has multiple applications, not, I mean, same brain, you have neurological, neuroscience application, lot of science questions on understanding of brain, you kind of use PET, right. Cardiac, tumor detection, right. So, several interesting things, just to reiterate that it is a functional imaging. Here what, so here is an experiment, image from an experiment, where when a participant is shown, right. So, he is reading from the text. So, when he is reading from the text, your visual cortex, right, you are looking at it. So, your brain that controls your vision part, that gets excited, activated. Okay. So, lot of activity happens here associated with reading, and therefore, this is lighted up. Whereas, the same thing, if the same content, if they are asked to hear through a earphone, right, they are not seeing, but they are hearing, a different part of the brain is getting active. So, all these, I mean, this is a cool image, right. So, it is borrowed from here, but the idea is you can functional imaging, we said what are the insights that we can get here. You can give radioactivity, you can see where high metabolic activity happens, right. So, here when I am reading, a different part of the brain is active, when I am listening, a different part of the brain is active, I can actually see where it is. Okay. So, these are very powerful, very beautiful modalities from a functional imaging perspective. So, you do not see the brain details that much, right, but then you can combine it with your CT, and then you can have a brain CT fused with your PET, you could get both the information, right. Okay. So, coming to the last part, which is the image quality aspect, we will not spend too much time on this, because lot of image quality aspects that we saw already is direct carry forward. The only thing is, here we talked about your collimator and then your detector part, that is the, so acquisition is different, right. Compared to your planar scintigraphy, you have multiple acquisitions and you are doing recon. So, only where, so we can actually formulate this as, oh, your ideal image, or there should be a hat here, this is an estimate, right. Estimate is your ideal image convolved with your HR. What is this HR? In case of SPECT, you have to include the response from your collimator and intrinsic resolution, we covered this, right. Collimator and intrinsic resolution. Apart from that, there is this filtering coefficient, filtered back projection, that effect. Okay. So, that will come into effect, and in your PET, the positron range function, that is a new thing that came. So, how your detection thresholds, right, timing window coincide, that is the only part that is new. So, that threshold could have an effect on the noise, and and also your resolution for that matter. So, your positron range, detector width, notice we kind of, we do not have one big detector, we have a blocks that we have done. So, detector width effect, of course, here also a ramp filter window effect will come. Okay. So, nothing really apart from this is very similar to what we covered in our planar scintigraphy image quality, same thing carries forward here. Okay. So, I think with respect to nuclear medicine, right, at the introduction level we have covered what we wanted to cover. To summarize, we covered 3 major modalities within nuclear medicine. What are they? Planar scintigraphy, SPECT and PET. Okay, all this we covered. What all we covered? First we talked about the most important aspect that is new here is your Anger camera, which had your collimator, scintillation crystal and then photomultiplier tube. Okay. We apart from that we talked about the imaging principle in planar scintigraphy and SPECT. The recall, right, we talked about how do we use your x comma y z pulse, that is an important concept when we talk about Anger camera. Okay. Apart from that, so we talked about the imaging principle here, and then essentially we argued here it's both gamma decay, that is what we are interested. So, for most part the T, right, SPECT, the T is very similar to your X-ray projection that we did and X-ray reconstruction, X-ray CT that we did. We could ignore the attenuation factor, which is routinely done, right. In most practical system attenuation factor is ignored, but we also see that it is an active area where you could do corrections. Okay. Likewise in PET, the important aspect principle of PET is apart here also you have gamma, but then the gamma is you have a positron. It says positron emission tomography, but then it is you are not catching the positron directly. This positron annihilates and give a gamma at 511 kilo electron volt. So, you are catching the gamma ray at 511 kilo electron volt. When I say that catching, you are catching 2 of them which are coincident. That is an important aspect that is different here, coincident detection. So, you have a threshold to say what is simultaneous, and that will allow you from differentiating that activity that you think is legitimately from the decay that is along the line connecting the detectors, or is it some random photon. So, once you have that, you get here you can differentiate or you can segregate your radioactivity terms and your mu terms. Therefore, you could correct here as well. Okay. So, simultaneously you can correct your A. So, you can get your corrected PET corrected for your mu distribution. Okay. Okay, you can get that from say for example PET CT that we talked about. Okay. So, I think this provides a reasonable introduction material on nuclear medicine and what is the physics, what is the instrumentation, what is the image reconstruction and what is the image quality. As you would notice, if you covered the first part, right, the recon in X-ray and physics in X-ray, from there to nuclear medicine we highlighted only the key differentiating aspects. Otherwise, this line of thinking about talking about physics, capturing the instrumentation to engineer that physics for an application, right, then your imaging equation and then your image quality is very similar. Okay. Let us stop here. Now, we will move out of the radiation and get into non-radiation, non-ionizing radiation based imaging modalities. Thank you.